Welcome to the third talk in this third day of the summer school. Today we have Karl Friston, who is the director of the Wellcome Center for Human Neuroimaging, Institute of Neurology, UCL London. He's a theoretical scientist, neuroscientist, and authority on brain imaging. He invented statistical parametric mapping called SPM, voxel-based morphometry called VBM, and dynamic causal modeling, DCM. Mathematical contributions include variational Laplacian procedures and generalized filtering for hierarchical Bayesian model inversion. Karl currently works on models of functional integration in the human brain and the principles that underlie neuronal interactions. His main contribution to theoretical neurology is a free energy principle for action and perception called active inference. Now, this is a summer school in which we've talked a lot about inference. So we're now going to hear from somebody for whom inference is sort of the core of his approach. Karl, welcome, and it's yours. Can you speak?
Yes, I can. Sorry. Thank you very much for the introduction. I'm just waiting for permission to share the screen.
Yes, I have to get you that permission. I have to get off myself. There, you'll have it.
Lovely. Thank you. Excellent. Well, let me start by thanking you for the opportunity to speak to you. I've learned an enormous amount about not only large language models, but language, and that probably reflects the fact I have no foundational training in language, so my apologies for that. And I should also confess I'm a large language model virgin. I've never actually used a large language model, but I feel slightly enticed to do so, having heard all about them. As such, I'm going to take a very narrow brief and just pursue some of the elemental aspects of communication and language as emergent properties of things that interact. And I'm going to premise this. Let me just put this in presentation mode. I'm going to premise the story. Incidentally, a story I think that Daniel Dennett would very happily subscribe to. I'm going to premise this story on a quote from Helmholtz that I'm reading as his take on symbol grounding and synchronization or harmony of the kind that I'm going to use to illustrate the way that we make sense of our world and our world makes sense of us. And sometimes that world can be another person to whom we are talking. So, no perceptions obtained by the senses are merely sensations impressed upon our nervous systems. A peculiar intellectual activity is required to pass from a nervous sensation to the conception of an external object, which has the sensation which the sensation has aroused. The sensations of our nerves of sense are mere symbols indicating certain external objects, and it is usually only after considerable practice that we acquire the power of drawing correct conclusions from our sensations respecting the corresponding objects. Now, much of what I'm going to say is based upon the insights and offerings, both mathematical and narrative, of Helmholtz. And I'm going to tell the story, the backstory to this observation in two ways. I'm going to start by just considering self-organization from the point of view of a physicist and talk technically about the statistics of life, and with a special emphasis on Markov blankets and inference, Bayesian mechanics of the kind that we've been discussing. And then I'm going to tell exactly the same story from the point of view of predictive coding and neuronal networks. And then I'm going to close by essentially finding the common theme here, which is this notion of synchronization and how it can be read in terms of many of the ideas that we've already heard about, for example, satisficing, for example, the importance of predictive coding in finding those minimum description length or minimum message length representations of the things that we are trying to infer in the world. So let me start with a question posed by Schrödinger. How can events in space and time, which take place within the spatial boundary of a living organism, be accounted for by physics and chemistry? Now, we're not going to answer that question, but what I want to do is just pick out the notion of a spatial boundary and emphasize that in order to talk about me or you or anything, I have to individuate myself from the rest of the universe. And I'm going to read that boundary in a statistical sense as a Markov blanket. And for those of you who are not familiar with the notion of Markov blankets, they're very simple. Let's take some abstract universe composed of various states of affairs. And these states can influence other states, and the influences are denoted by these little arrows here. And if I identify some set of states, say my states, then my Markov blanket, the blanket states, comprises the children, the parents, the children, and the parents of the children. And the role of these states is to separate me in a certain sense from the rest of the world. Technically, the internal states are conditionally independent of the external states if I knew the boundary states or the blanket states. And what that just means is that all the information about the rest of the universe that is needed to predict how I am going to evolve is contained on these boundary states, on my blanket states. And I'm going to make a further move here, which will be evident why I'm doing that in the next slide. I'm just going to divide the blanket states into sensory states that influence but are not influenced by the internal states, and active states that influence but are not influenced by the external states. And so with this particular partition, I've now got a mathematical description of some entity, something, some particle, some person that possesses internal states and their blanket states, where the blanket states can be divided into sensory and active states. So why sensory and active states? Well, if we think of my brain as the thing in question, I can ascribe all my internal neuronal and synaptic states to the internal states. And then these internal states influence the active states, say my actuators, my autonomic reflexes, my muscles, that in turn influence but are not influenced by the external states. Could be my physiological states, it could be states of extrapersonal space, it could be your states. And these external states in turn influence the sensory states, so I'll say my sensory epithelia, my interoception, that then influence the internal states but are not influenced by the internal states. So what I have here is a mathematical image of effectively a system that has inputs and outputs so that the inside influences the outside vicariously through the active states, while the outside influences the inside through the sensory states. If you like systems theory, all we're doing really is defining a system, in this instance, a brain, in terms of its inputs and outputs. And that is sufficient now to talk about something as distinct from everything or nothing. What I want you to do now, though, is just to forget about the Markov blanket for a moment. We're going to do a very brief crash course in physics, and then put the Markov blanket back into play and see what happens. The physics we're going to briefly rehearse starts off with a universal description of any random dynamical system or universe in terms of changes in the states of this universe that depend lawfully on where I am, the state that I'm currently in, plus some random fluctuations. And I've cartooned that here in terms of a trajectory through some arbitrary state space. You can have any space or time scale. For example, it could be the oscillation of a cell in my hippocampus. It could be my cardiac cycle or my respiratory cycle, or it could be me getting up in the morning and having a cup of coffee, doing my emails and so forth, or it could be a life cycle. The key aspect is that if I can be described, or any system can be described in this way, it keeps on returning to the neighborhood of states that it was once in. Technically, this is called a pullback attractor, or more simply just an attracting set of states that characterize the kind of thing that I am. I am much more likely to be found in this state than this state. And indeed, if I was found in this state, I wouldn't exist in the form or the kind of thing that I am. And I'm going to leverage that interpretation just by thinking of these trajectories or their density in terms of the probability that you would find me in this state, given I am me. And I'm going to use that interpretation now because we know a lot, or physics knows a lot, about how this probability density changes over time. I've written this down in terms of a Fokker-Planck equation. There are lots of other ways I could have written it down. The maths doesn't really matter here. The key point is that we know there's a lawful relationship between the way these densities change over time, given that they exist, given that I exist, and the amplitude of the random fluctuations and the dynamics or the flow that characterize this trajectory. However, I've just said that this density does not change with time because we keep revisiting the same states. So the rate of change, the density dynamics, is zero, which means I can solve this equation, and people do this a lot. This is a solution due to Helmholtz that is in a way that is very revealing. What it tells us is that my dynamics, the way in which my states change, must be expressed effectively as a gradient flow on this quantity here. And this quantity is just the log probability of finding me in any particular state. The negative of this is self-information, but we will take a number of different perspectives on this in a second. But I want to emphasize here that this composition due to Helmholtz has two bits. It has this sort of gradient flow. It looks as if this quantity is being maximized. But there's also a quantity here known as conservative flow, or solenoidal flow, which gives a biological or biotic, at least biomimetic aspect to the dynamics. It means that there's going to be cycles in play in virtue of this conservative part of the flow. And we will all be very familiar with this kind of separation into downward flow here due to gravity as this water flows out of the bath, but also the circular flow as it swirls around during its descent. And that's just what that Helmholtz decomposition describes. So what about the Markov blanket? That law, that rule that applies to any system that possesses characteristic states, that has this attracting set, must hold for all the partition of the Markov blanket, including my internal states and my active states. So what does that mean? Well, it looks as if my internal states and the way that I act upon the world is changing in a way to maximize this quantity here, this log probability of states given me, for example. Here, the sensory states. And notice by construction, because the external states do not influence the internal active states, this is just a function of my sensory states, of the sensory sector of my Markov blanket. And what I'm going to say, or try and convince you of, that this is a very simple mathematical expression of perception and action. So what explanations or interpretations can we afford this log probability of sensory states given me? Well, I've just said that these are part of the attracting set. These are the states that are characteristic of me, that it looks as if I aspire to these attracting sets. They have value for me because they define the kind of thing I am. So we can read this formulation of perception and action in terms of maximizing value. And from that, we could spin off reinforcement learning stories in behavioral psychology. If I was an engineer, This would be a statement of optimal control theory. If I was an economist, it would be a statement of expected utility theory. Another perspective would be afforded by looking at this from the point of view of somebody doing information theory. So the negative of this kind of value, the plausibility of you finding me in my characteristic states, in my attracting set, is called self-information in information theory, sometimes surprisal, more simply surprise. It just scores the unlikeliness, the implausibility that I would be found in this particular state. And what this says is that both internal and active states are trying to minimize surprise. And from this, we can read off things like the principle of maximum mutual information, minimum redundancy, and the free energy principle. And just an interesting point here that this, I think, relates very, very closely to the arguments we were hearing before about minimum description length. We can get into the maths, and there are many ways of expressing this in terms of things like algorithmic complexity, which we're trying to minimize to maximize the efficiency or minimize the redundancy. And that leads through to what we were talking about earlier on in terms of Solomov induction and indeed universal computation. It's also isomorphic with the free energy principle, because the free energy principle is effectively a mathematical score of the surprise or the surprisal that we're trying to minimize. And it looks as if we are minimizing. The average of surprise is entropy, which means that action and perception, so articulated, look as if they're trying to minimize entropy, the dispersion of my states. And of course, this is a holy grail of the physics of non-equilibria. For example, synergetics of the kind introduced by Hermann Haken. But if I was a physiologist, it would just be a statement of homeostasis. It's just trying to keep my central variables within physiologically viable bounds to stop them dispersing through these gradient flows that counter the random fluctuations. There's a final interpretation here, which I want to leverage. It's an interpretation that a statistician would bring to the table. She would interpret this quantity as the probability or the likelihood of some sensory data given not me, but me as a model of how those data were caused. And this is called model evidence in Bayesian statistics. And what this means is that perception and action is trying to maximize, or looks as if it is trying to maximize model evidence. Some people like to call this self-evidencing. From this, we can motivate the Bayesian brain hypothesis, evidence accumulation, and things like predictive coding. And indeed, I will sort of unpack the predictive coding interpretation later on. So this simple consequence of possessing in a sustainable way characteristic states in the context of me being separate from the rest of the universe leads to a number of internally consistent views on self-organization. Just to give you a numerical example of the kind of behavior that one emerges from this kind of formulation, what we've done here is simulate several hundred little macromolecules that are equipped with strong repulsion and weak electrochemical attraction. And the reason that we did this is that we wrote down those equations of motion, those dynamics, technically a Langevin equation. And in so doing, we know exactly what influences what, and now we can identify a set of internal states, for example, and their Markov blanket, and ask, is there a little thing, is there a little subsystem living in this synthetic primordial soup? And indeed there is. This is exactly the same simulation, but what I've done here is color code the molecules in terms of external molecules in cyan, the sensory molecules or states in magenta that overlay the active states in red that encompass the internal states. And what we have is a little sort of viral light particle wiggling around, attaining what's technically known as a non-equilibrium steady-state relationship to its external world. So the question now, if this Bayesian interpretation, if this self-evidencing interpretation of the internal and active states is true, then it should be evident that the internal states in some way represent the external states, mathematically hold Bayesian beliefs about the external states. So is there any evidence that that is the case in this simulation? And there's ample evidence. This is one example where what we've done is we've taken a linear mixture of the internal states, say a neural population in my brain, and asked, is there any coupling, any representation of a probabilistic sort of the motion of the external states? You know, for example, visual motion, if I was doing studying visually evoked potentials. And what we see is that there is a very, very accurate reconstruction at this non-equilibrium steady state, illustrated here by the prediction based upon the internal states with 90% Bayesian credible intervals and the actual fluctuation of the motion on the outside. And this is quite remarkable because remember, these external dynamics, these external states can't directly influence these internal states. These can only be seen through the blanket states and through the sensory veil, effectively, that encompasses these internal states. If I now group together the peaks of these fluctuations when these little molecules are spat out into the periphery and then are pulled back in again, we get something that looks remarkably like event-related potentials in electrophysiology research. Here's an empirical example from a small animal study. And here are the same data here. So what are we looking at here? In a sense, we're looking at something which has been well known for many centuries. We're looking at a synchronization of chaos, or some people call it generalized synchronization of the kind first noted by Christian Huygens, who was the man who noted that if two or more clocks are suspended from the same wall or the same beam, they will inevitably start to swing in synchrony. So they collapse to a synchronization manifold. And here's a drawing from Huygens here of two clocks suspended from the same beam. And from our point of view, we can regard one of the clocks as possessing the internal states and the other clock as the external states, the environment, and the blanket states are constituted by the beam that couples these two sets of separable states. I like this drawing because it emphasizes the mathematical symmetry. So if you subscribe to the view that your internal states are somehow representing or inferring your external states, then it must also be the case that the environment is inferring and trying to learn about you. And that's not a silly notion in terms of niche construction and the like, but that's not the subject of today's presentation. So what I'm going to do now is effectively tell exactly the same story, but not now from the point of view of physics, but from the point of view of psychology, computational neuroscience, and neurobiology, and particularly tell a story about predictive coding and how that might play out on neuronal networks. And this story probably goes right back to the students of Plato. I'm picking out an example from the 16th century here, afforded by this oil painter famed for painting still lives, that when viewed from another perspective, give you a very different visual impression. So if previously you saw a bowl of fruit, and now you see a face, the point he's making here is that you made that face. You brought this as a hypothesis or an explanation to the table to explain this particular pattern of sensory impressions. And indeed, we've heard the phrase earlier on today, inference to the best explanation. And I think this is exactly what this example and this artist was trying to communicate. People like Andy Clark would say that the brain is a statistical organ. It's a constructive organ, generating predictions, explanations, fantasies in an inside-out kind of way to try and make the best sense of the sensory impressions. And on that view, the brain is literally a fantastic organ, a purveyor of fantasies, apt for trying to describe and make sense of what's going out there in terms of what is causing the sensations. And of course, this idea was articulated beautifully by Helmholtz. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. Again, what it's saying, it has to be on the inside. It has to, you have to have the percept or the explanation, the hypothesis, in order to use the sensory data either to confirm or disconfirm your hypothesis. And of course, that is very close to the notion of people like, say, Richard Gregory in terms of perception or as hypothesis testing. And this basic notion has been used to great effect by many people. I'm just picking out here an influential application of these ideas by people like Geoffrey Hinton and Peter Dayan. Indeed, they built a Helmholtz machine as a metaphor for the Bayesian brain, borrowing from Bayesian probability theory, and in particular, the work of Richard Feynman in finessing the mathematical problem of doing this kind of Bayesian inference. But let's just come back to Helmholtz and the notion of impressions on the nervous mechanism, impressions on the sensory sector of my boundary or blanket states, my sensory veil that separates me on the inside of my brain from the outside. And if this notion of self-evidencing, the Bayesian mechanics that emerges from possessing a Markov blanket is true, what that means is one explanation for what's going on inside my head is that I am compelled to represent or infer, find the best explanation for the causes of these sensory impressions or shadows. So how could my brain be doing that? Well, we already know how it's doing that because my brain has to conform to this fundamental gradient flow, this Helmholtz decomposition, where the gradients now expressed in terms of gradients on the free energy form of the surprise or self-information. And what I've done here is interpret the internal states as standing in for the parameters of some Bayesian beliefs and posterior or approximate posterior beliefs about the external states. Furthermore, what I've done is rearrange this equation into a form that if you were an engineer, you would recognize, or you might recognize as something called a Bayesian filter or a Kalman filter. And all I've done is say, associate the solenoidal part with a prediction. So what does that mean? Well, if I have some expectation, some representation of the state of affairs out there causing my sensations, I also have a prediction about how those predictions are, how those states of affairs are going to change, the rate of change. That's what the dot means there. So I have a prediction about what I'm going to see next. But I also have the opportunity to use my free energy gradients to update that prediction by associating or interpreting these free energy gradients as a prediction error. So what's a prediction error? Well, imagine I had this sensory impression on my retina or some sensory epithelia, and I had an expectation that it was caused by a howling dog. And if I had a generative model of what I would see if indeed my expectations were correct, I can generate a prediction of what I would see and compare it with what I'm actually seeing. And the prediction error is simply the difference. It's simply the mismatch between my sensory input and that predicted under a generative model, given my current beliefs. And all this equation is saying is that the prediction error is then used to change or drive my beliefs to provide a better explanation until the prediction error is suppressed or minimized, and I found the minimum of my free energy, at which point the gradient disappears. So notice all we're describing here is a minimization of prediction error. We won't actually know what's happening or what actually caused our sensations, but that doesn't matter. If we can keep our prediction errors small, then that is sufficient. That satisfies us. So we can forget about all the physics and now just reduce the imperative for existence in terms of minimizing prediction error. And that's nice because there are two ways in which I can minimize my prediction error. I can either change my mind to make my predictions more like my sensations, or I can act upon the world to sample those sensations that are more like my predictions. So this provides a very parsimonious view of action and perception, that they're both in the service of minimizing surprise, free energy, prediction error, either by changing the predictions or by actively sampling the world to try and make those predictions come true. So here's a slightly more neurobiologically plausible example of that, looking at the visual system. So imagine we had some visual input from the retina, and it comes in, say, to the lateral geniculate bodies, and it's in receipt of some top-down predictions from early visual cortex. And the sensory inputs and the top-down predictions are then used to form a prediction error, according to this equation. And then this prediction error, according to this fundamental gradient flow, is going to be used to update, revise, improve my expectations so that this prediction error is minimized. But of course, these expectations can also be predicted by a second order or a higher order area, say V2. So that's sending down predictions. It's compared with the actual expectations at this level. We have the second order prediction error that then is passed up. So all I'm describing is a hierarchical predictive coding network of the kind that fits very comfortably with what we know about the neuroanatomy and the physiology and the laminar specificity of extrinsic connections in the visual cortical hierarchy. What I want to do now, though, is just consider another kind of input that emphasizes the bilateral ways in which we can minimize prediction error, namely the active part. Imagine I had another kind of input that was from my oculomotor system, from my eye muscles, say, reporting the degree to which they were stretched. And this proprioceptive input will come in, say, to the pontine nuclei. It would be met by top-down predictions, say, ultimately from the frontal eye fields. So I could form a prediction error. Now, I can eliminate this prediction error in one of two ways. I can either use it to change my mind about where my eyes are pointing, or more simply, I can simply send that prediction error back out into the outside world to cause it to contract the muscle until the muscle reports the same as that which I predicted. And this, of course, is just a classical reflex arc. It's how we actually move our bodies, and you can also generalize this to the control of our autonomic nervous systems. And what we're saying here, that this kind of action, or this inactive formulation of predictive coding, is very simple. All we're saying is that this deep hierarchical processing that assimilates all the evidence and tries to make sense of it under this hierarchical predictive coding or Bayesian inference kind of architecture is just in the service of predicting how I'm going to move next. And these predictions provide set points that are fulfilled reflexively through classical peripheral reflex arcs in a closed loop system. But the predictions inherit from a very open loop, a lot of deep processing. So that's basically predictive coding with reflexes, described by many people, probably first by people like David Mumford, in terms of the anatomy of belief updating in the brain. I'm now going to close with a couple of examples and try to now show how this would lead to a certain kind of synchronization, which would characterize or be one key aspect of communicative interactions between two things that were sufficiently similar to conspecifics, or certainly shared the same narrative or same generative model. And the agenda here is really just to sort of show you another example, another numerical example of synchronization of chaos of generalized synchrony, but now has all the hallmarks of communicative interaction. So before we do that, though, let's just look at an example which foregrounds the circular causality that is inherent in this picture of how we establish and sense make this, that rests explicitly on this inactive component. So what we've done here is simulate movement, handwriting, and its observation by equipping a synthetic agent with an expressive generative model based upon a central pattern generator. And this agent thinks that this abstract movement is mapped to a point, an invisible point in extrapersonal space. And furthermore, this point is attached to the end of the agent's finger by an invisible spring. So the agent is now generating predictions, both of what the agent expects to feel in terms of feeling the finger being pulled around, and also what the agent expects to see in terms of seeing the finger being pulled around. But because the agent's equipped with reflexes, those feelings are fulfilled, and indeed the agent's finger is actually pulled around, thereby generating the predicted visual input. And this is the ensuing synthetic handwriting that is caused by this just by integrating those fundamental equations of motion, that gradient flow, which you can read as a predictive coding scheme. And it produces a lot of phenomena which we'll all be familiar with, certainly as neurobiologists. What I've done here is just plot the activity of this unit here whenever it exceeds half maximum as a function of where the finger is in space. And we evince a characteristic specificity, a receptive field, for example, a place cell-like response profile, that in fact also shows a direction selectivity in terms of preferring the downstrokes to the upstrokes. Interestingly, what we can do is we can remove the proprioceptive input, but retain the visual input. So from the agent's point of view, it would be like seeing the same thing, but with no sensory evidence that the agent actually caused this. So it would be as if somebody else is doing the writing. But the agent already has exactly the right mechanics and the right intrinsic dynamics and architecture to predict that writing, and can very quickly use exactly the same machinery to confirm the visual predictions. So this is action, and this is observing the same action, but without any action sensations. And what we see is that the agent indeed does use the same representation. Takes a little bit longer for the agent to recognize the particular J and A writing here, providing a very simple numerical model of mirror neuron activity during action observation. I want to close, though, with the denouement of these emerging behaviors that rest really upon the interaction between two of these systems that are being understood in terms of predictive coding or making inferences of an efficient sort about the causes of their sensorium. And what we've done here is effectively create two little birds, where each bird has one of these central pattern generators that has this deep structure to generate predictions of heard song. And I don't know if you can hear this. I can hear it. It's very sweet. So what we've built a little synthetic songbird, and what we're going to do basically is to use those equations of motion that must be the case for anything that has an attracting set, but in this instance, put two things together, and they're both trying to minimize their surprise. They're both trying to minimize their prediction errors, and the way that they're going to do that is by committing to the same generative model, so that as they are singing, they are also expecting to hear not only what they are singing, but also what the other bird is singing, provided that they can hear each other. So here's a simulation of a situation in which the two birds are generating their own song. They're both singing alone, but they can't hear each other. So they're not in a position to be able to predict the entire sensorium. I should say that in these simulations, one bird, first of all, only one bird is allowed to sing at any one time, using that removal of the proprioceptive input that was illustrated in the previous handwriting example. So what would happen if we now put them in a situation where they could prompt each other or they could hear each other? And if I move the birds together within hearing range, then what we see is now exactly this synchronization of chaos that we were illustrating using simulations of the primordial soup. So the point being made here is that we have an example where a plausible interpretation of this generalized synchrony is in terms of two birds singing to each other with a language that is predicated on a common generative model whose emergence can be sufficiently explained by minimizing prediction error or minimizing surprise, that itself can also be interpreted in terms of finding explanations, inferences to the best prediction for the causes of sensations, which in this instance, the one bird was the other bird, and symmetrically vice versa. So here's the synchronization manifold depicted when they can't hear each other and when they can hear each other, just to show how they align in a certain kind of harmony where everything is now mutually predictable and in one sense mutually understandable, because they have this this synchronized dynamics inherent in their two generative models.
So,
just a nod.
Karl, was your prior illustration meant to be something that we could hear?
This was, yes.
But we didn't hear it.
Oh, my apologies.
Well, it may not be remediable, but then what you have to do is describe what we would have heard, because we didn't hear anything.
I thought you were going to ask me to imitate it.
You could.
Which I can't do, but I speak, I have a slightly dry mouth, so because I'm slightly nervous, so I can't whistle. But what I am hearing is a very sweet little bird going tweet 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 tweet. Not when they can't hear each other, they're completely out of phase. But as soon as they can hear each other, they accompany each other, and there's lock phase. So it's having two little birds singing to each other, and crucially, they take it in turns, and this is what the blue and the red are pink and blue here are meant to indicate, so that one bird is picking up from the other bird in succession as if they were singing from the same hymn sheet. And that's what I'm hearing. So I'm quite happy, but I'm very, yes, this never works on Zoom for some reason. It's not, you know, this doesn't come across. But trust me, they sound very happy and in harmony. And yeah, I was just wanted to nod to my colleague Takua, who's taken this kind of synchronization through communication and interaction, and emphasizing the active aspect of this to sort of develop a theory of social intelligence. But what I want to do is to come back to this notion of being in harmony through a shared narrative, a shared generative model that grounds you in the way that you can now represent what's going on out there. And of course, when what's going on out there is somebody doing exactly the same thing in terms of trying to understand you, you have this notion of synchronization or harmony. So I'm just going to very briefly reread where we started. No perceptions obtained by the senses are merely sensations impressed on our nervous systems. A peculiar intellectual activity is required to pass from a nervous sensation to the conception of an external object. And I think we can read this as the inference to the best explanation, abductive inference that is as efficient as possible, that has this minimum description length aspect or minimum complexity that underwrites sufficing, which the sensation has evoked or aroused. And the sensations of our nerves of sense are mere symbols. They are the internal neural dynamics are representations or encoding Bayesian or conditional probabilistic beliefs about something outside. And it is usually only after considerable practice, emphasizing the developmental and inactive underpinnings of this kind of competence, that we acquire the power of drawing correct conclusions from our sensations, respecting the corresponding objects. And that's from On the Physiological Causes of Harmony. So all that remains is for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you. Thank you very much indeed.
Okay, the first question is from Steve Hansen. Steve, turn on your sound. While Stephen figures that out. You have to put on your sound. I don't know what to do about that. In the meanwhile, to get the discussion going among everybody, I'll ask you a question that you've probably been asked many times before. We know that in physics, there are interactions between dynamical systems. So it's not new that there are interactions. What extra, and I warn you that when you answer this question, you're essentially giving a theory that is meant to be the solution of the so-called hard problem. But why is it that some of these interactions involve prediction and expectation rather than just causation and interaction? That's it. That's the first question.
Right. I think the best way of responding to that would be to say, in terms of the story I was telling about predictive coding, it is just a story. It's a teleological interpretation of the causal dynamics. So what that sort of formulation, the free energy principle, just brings to the table is a license to talk about prediction and Bayesian beliefs in a way that ascribes a certain teleological function to a description of the underlying causal dynamics. So there's no pretense that that the actual dynamics on the inside of anything, including my brain, is doing prediction. It's just I can describe it as such. And in fact, there's an interesting implication of the free energy principle, which means that because the internal states of something that is being observed are unknowable, because everything that you can observe in terms of this thing is expressed on its surface or its Markov boundary, that means you can never know what something else is doing or thinking. All you can do is infer that it looks as if this thing is sense-making or doing predictive coding, or is behaving in a way that evinces that kind of predictive processing. So that would be, I think, a sort of deflationary answer. It's just a story. It's just an interpretation of the underlying causal dynamics. But you could go a bit further and say, well, what kind of internal interpretation would lead to consciousness? And I think you'd have to qualify then the different kinds of things and different kinds of implicit generative models that could or could not be conscious, or from your perspective may or may not be sentient. But I think that's a different discussion. I didn't get.
Actually, it's the same discussion, but that's okay. It's the same discussion because what you said was that I asked what more do we need than the causal story? And you said, well, this is not adding more. This is just something that it's an interpretation of the causal story that fits. And I can give examples to show that sentience is part of it. I know what it feels like to expect something, to predict something, and to have the prediction not met, and not, etc. So those are all felt states. And the question is, what on earth are they for? If all you have is a causal story that can be, by us feeling creatures, given a felt interpretation.
No, you're tempting me to answer that. Yeah, so that's the fact you know means that your generative model has to have a model of yourself and self as agent. I think that's the bright line I was trying to speak to.
The other way of saying that would be that your model would have to have that if my interpretation were actually something other than just an interpretation.
Yes, absolutely.
Okay. There is a question here. Do the songbirds still change their songs if they each already make a repetitive sound that fits each other, like align, mod each other, so that the combination with no changes would already be easy to predict? Apologies if I'm misunderstanding. That's Julia Zimmerman saying that. Julia, do you want to say it in person? Anyway, did that make enough sense to you so you can say something about it?
Yes, I think so. Yes, they certainly align in the service of mutual predictability. So the story here, or the idea here, is that you train each other. By in conversation, you effectively have a kind of generalized synchrony whereby you're both working through the same narrative or trajectories, but in a way that now becomes entrained and coupled through the sensory exchange. And that means that as you work through these very itinerant trajectories, so the birdsong itself has quite a deep hierarchical structure. It's not just a sort of regular periodic tweeting. There are phrases and narratives with this deep temporal structure. And where you are in this narrative now becomes aligned with the other bird, so that you, I repeat, are literally singing from the same hymn sheet, so that my behavior becomes your behavior, and it becomes our behavior, or overt behavior, so that the only thing that's left for me to infer is whose turn is it to actually talk, or put it another way, the only thing that I now need to infer is to attribute the agency, who's actually doing the talking at the moment, because I know exactly what you're saying because it's what I'm saying, and vice versa.
I have to speak aloud to Steve Hansen, who's trying desperately to ask you a question, but he's not getting any success. I assume that Steve Hansen hears me speaking, even if he cannot himself speak and he cannot show his face. What the technician says is that nothing has changed since you were successful in doing that earlier this week. So if there has been a change in configuration, it's not on this end. So I can't respond to your tech either. You guys have control of my audio and video, just turn it on. No, well, anyway, there's nothing I can do with that. So I have to continue with with what you were discussing. What? Is there another question? Where?
Yeah.
One sec, I'll have
I assume
Go ahead.
it's Gary. Yeah. Thank you for the talk. I'm wondering if you can speak to how you view the relationship between prediction and intelligence. So there is one perspective that views intelligence, sort of defines intelligence in terms of maximization of reward or lowering prediction error. Alternatively, one could view that as being the mechanism by which intelligence arises. So just wondering if you can speak to how you view this theoretical construct of intelligence.
I guess from the point of view of artificial intelligence or natural intelligence, I think we're probably in the game of talking about the intelligence of things that possess a non-trivial agency. So that immediately calls to mind questions about the distinction between, for example, what's governor or a thermostat or a virus and you and me. What characterizes would you call a thermostat intelligent? I mean, it certainly has purpose, it certainly has a goal, but does it can you interpret it really as evincing a true kind of intelligence? And I would argue probably not. So what's the difference between a thermostat and you and me? And I think that the simple answer is that we plan. So that comes back to where you started with your question, which was this notion of prediction as forecasting. So now your generative model acquires a temporal depth. So now there is a horizon. It's interesting you mentioned reward, because of course that always comes equipped with a future horizon. So I think it's quite important to acknowledge that we're sort of when the prediction becomes future pointing, I think we move away from simple reflexive, merely reflexive kind of self-organization and into the realm of self-evidencing with true agency, in the sense that there is a notion of a counterfactual future that an agent can cause. Just to speak to Stefan's point, if there's a model of me causing that future as well, then there may be some consciousness or true self-awareness. So I would say that the kind of prediction that underwrites truly or authentically intelligent behavior rests upon having a generative model that includes the consequences of your own action. And then that affords the opportunity now to roll out into the future and select among a number of counterfactual futures, each of which is underwritten by a particular policy. And that in turn involves a Bayesian model selection, or a selection of the best kind of policy. So I think that's where it starts to get a little bit closer to sort of vanilla reinforcement or rewarding schedules, as a sense of a discounted reward in the future. It's not quite how active inference works, but it has the same sort of architecture. That there is this futuristic, anticipatory, prospective aspect to both effectively to planning, and that's very different from the kind of predictive coding that you read about that would be entirely fit for purpose in describing, I repeat, a thermostat. I mean, the prediction of a thermostat is the predicted temperature at which I expect to exist, and I just act upon the world in order to bring it back to the predicted one. But I think you're talking about a much more agentic kind of prediction.
Okay, let's wait a second, Gary, because you had no problem at all getting through. Steve did, and he did the unexpected, and he seems to have appeared. Can you also talk?
I don't know, can I?
Yes, go ahead.
Well, look at that. That's amazing. Hi, Karl. How are you? That was a wonderful talk. I've actually heard this talk at least once before, but and I've always liked the Markov blanket kind of setup you have here. It's very interesting. Now, this is the Markov blanket in the sense of Judea Pearl, right? So this is I'm going to take an acyclic graph, and then I'm going to find some rules to make boundaries on the graph. And as you say, the parents, the children, the children. This seems like an interesting mechanism if we go back to your other line of work with brain imaging, to do parcelization of the brain. If one, laid over like a Thomas Yo kind of 1,000-node parcellization, and then tried to compute Markov blankets on this thing according to some kind of criterion. Obviously, the criterion can vary quite a bit. It also struck me, before I let you comment on that, that one could use this in the attention heads of an LLM. I understand you haven't used LLMs before, so that may be confusing, but the attention heads are the part of the GPT, that the LLM, that basically are autoregressive. They're really just autoregressive structures. And there's been recent proof showing that, in fact, they can emulate a recurrent neural network, a very, very deep RNN. So the dynamics that you're talking about are clearly inside this thing. And that's a very interesting application, because there's another number of people in this summer school and elsewhere that are looking at circuit structure inside of the LLM, sort of like divining it, or digging for gold to find them. Wouldn't it be interesting to maybe use a Markov blanket in this story to try to fit boundaries across these attention heads and pull out more structure? Because the structure seems to be very similar to what neuroscientists, you may or may not agree, friends of mine in the building here who work on single neurons or hundreds of neurons at a time for the next 40 centuries, right? So they're going to find a hard time generating a functional account of how we order lunch, much less else, in my view, but you may disagree. So that was my thoughts.
Yeah, two sets of great thoughts there. So yeah, likewise, I thought there was a very seductive opportunity to apply Markov blankets empirically to try and parcellate at different scales the brain. And in fact, I spent about 6 months doing so, and wrote it up. It's called. I think it was in network neuroscience. It's called Parcels and Particles in the Brain.
Okay.
And it does that at different scales. So the whole point of Markov blankets is that there's no one unique Markov blanket. You can just identify a certain set of internal states of interest at any particular scale, find the Markov blanket, repeat that for the remaining external states, and then just tessellate at this scale. And then you find Markov blankets and Markov blankets and move up scales. So it was a really seductive, really interesting exercise applied to fMRI time series. And if you look at the paper, my favorite bit is you were able to empirically estimate what's known as a renormalization group flow, a scaling law, which allows you to associate certain time and space scales to the functional anatomy of the brain. The problem was it was just so complicated. We couldn't find anybody really who was ever going to use it. And even if they could use it, it was so specific to an individual time series that it wasn't a useful data analysis device. But it was really entertaining. The second thing, though, again, it's a great point that I was just thinking, listening to some of the conversations about large language models, I can see in a few years there will be a journal of the cognitive neuroscience of large language models and all the skills. And people were asking, is it worth studying LLM theory and understanding this? And I thought, this is exactly what we do in neuroscience. We just take this large neuronal network and try and ping it and measure it and sort of look at its anatomy and understand the computational architecture. There's absolutely no difference. I can guarantee all of these analysis techniques that have been applied either at a small scale or in neuroimaging will be applied. And I think you're absolutely right. For me, one of the biggest clues to certainly the macroscopic functional architecture has been discerning the hierarchical structure. And of course, what defines a hierarchy? It's just the Markov blankets that impose a conditional independence between the different levels. So, in a more sort of generic sense, the Markov blankets are, if you like, just a technical way of specifying the kind of sparsity structure that just is the designation of a deep architecture, and all the factorization or a Fodorian modularization, if you like. It's all about the Markov blankets and trying to find those conditional independencies. So I think you're absolutely right. Yeah.
That's right. In fact, you could imagine doing a deep learning kind of extraction, if you will, using hidden Markov blankets as they maybe recursively cover some space. But now, is it the case the Markov blanket itself, do the nodes, can you have conditional dependence within the Markov blanket? In other words, I assume the factoring produces these conditionally independent things, but inside the blanket, could you have high dependency structure that you could fit from the boundary that you find? In other words, could you go back and, if you know what I'm trying to say here?
Yeah, well, I mean, I think in a sense that is the Bayesian mechanics that inherits from the free energy principle, that is understanding the coupling between the blanket and the internal dynamics. But I was reading your question is slightly more subtle than that, because you can have nesting of the Markov blanket, so that same story carries all the way down or all the way in.
Right.
And it
so
also
away from finite state machines to maybe context-free grammar within the Markov blanket. That's sort of where I was going with that.
In principle, yeah. I mean, if I'm reading context-free grammars in the right kind of way, but certainly
something with a stack. Something with a stack.
It's because the tendency at any space time scale, including structural learning, including evolution, including sort of developmental learning, including sort of in the moment inference, it's all predicated on maximizing model evidence. Then it certainly will have the structure of the model will entail a particular grammar and a particular message passing that will be the most efficient. If I read efficiency as that which maximizes accuracy whilst minimizing complexity.
Yeah.
So to me, all of these objective functions, whether they're sort of Kolmogorov complexity measures, or whether they're sort of minimum description length or minimum message length, or whether they're maximum marginal likelihood.
Ake, on and on. Yeah.
Yeah. And they should all, when optimized, give you the perfect universal grammar to explain your world, or at least articulate and interact with your world. Yeah, in principle.
Sounds interesting. Thank you.
Let's make it less esoteric. Julia, do you want to ask your question, or Anna? Either of you.
I was just wondering, based on what you guys were just saying, like, could you, if you have a bunch of linguistic data, can you use Markov blankets to find the boundaries that bracketing would find, like the hierarchical structure that occurs there?
Yeah, in principle, absolutely. I mean, that would be one. You'd have to. I mean, what you are asking is what is the right generative model that would properly explain or predict or provide an account of language. But certainly that specific aspect of bracketing has been addressed in both analytical and in numerical studies, not at the level of language, which you're probably interested in, but just at the level of segmentation, segmenting speech audio files. So, if I've got a continuous stream, say, time frequency stream from an audio file, I've now got I now have the problem of segmenting into, say, phonemes. And there are multiple hypotheses, the multiple ways I can do that. And that now effectively presents as a Bayesian model comparison problem, where the models are basically different alternative ways of doing the segmentation. So it's a kind of bracketing. And then if you can solve that problem, basically by actually using something that is mathematically very similar to attention heads in transformers, when you're reading the deployment of an attention head as doing a kind of Bayesian model selection, or highlighting this particular thing. If you can solve that, then you can just rinse, wash, and repeat at the next level, and then I think you'd be very much closer then to the bracketing notion. So yeah, in one sense, finding the deep compositionality in time of certainly spoken language is exactly the problem of finding the right generative model and then inverting that generative model to infer the right, to infer the structure in terms of successively coarse-grained representations that would be that would be fit for purpose for generating that particular speech, for example.
Anna Strasser has a question, but before that, I forgot Virginia Valiant, who had one even earlier. Virginia, you want to do yours first?
No, I'll wait. Thank you.
Okay, Anna, go ahead.
Okay, can you give me any allowance to show my video as well?
Yes, definitely. But how do we, what has to be done?
Yes.
Okay, but you're about to get. Have you known? Okay, it's coming in. Go ahead.
Okay. Hi. Hi, Karl. Maybe you remember me. So we had a conference at the Berlin School of Mind and Brain ages ago about predictive coding, and I'm still very fascinated with your story, and I loved your talk. And additionally, I have to say, it's great to see a person who claims that he is a virgin with respect to large language models. I think this is a very fresh perspective you can put on the whole thing, because all the other people are sort of drawn into the anthropomorphizing things which happen to people who are interacting with LLMs. So my question is, maybe a little bit misled, but I will try, and I'm curious what you're going to say. So if we try to apply the interpretation of a causal story to large language models, I think it's easy to apply it if you just look at the training phase of a large language model, where it is using the self-attention mechanism, and there we can tell a story in the language of predictive coding. But if we analyze the interactions between a large language model and a human, there I'm getting very skeptical whether this kind of story helps, because it might be questionable whether we can say something that there is a mutual predicting happening. So what I would say is, if I interact with a large language model, I interact with something what I metaphorically would call frozen intelligence. So this is not moving anymore. It's like, so I'm playing with a frozen thing, and then the predictive coding story doesn't help me anymore, because I'm interacting with something what is not interacting with me. What is your thought about that?
Well, I agree entirely. I mean, in a sense, that's why I was trying to emphasize the circular causality you get with action. And of course, the issue with large language models is they're not agents. They don't act. So as a neuroscientist, I'd be more interested in studying the prompt engineer than the large language model, because the prompt engineer is doing the action, the foraging for information, pinging the world to see what happens. But the large language model doesn't. So I think frozen intelligence is a really nice way of stating that. There is no agency in play. There's no there's no responding to any kind of affordance. So the inactive aspect of predictive processing, I think, would have very little to say about large language models. I can give you a cheeky answer. I mean, just to pick up on one of the assertions or suggestions earlier on, can we not use large language models as evidence for a particular kind of self-organization and belief updating? I think you can. But you'd have to treat them as evidence of a particular kind of cultural niche construction. These are artifacts, like books or word processors or spell checkers, and you have to ask yourself, why are they still around? Because if they survive in characteristic states, that means that you have to explain why, and assume that they are still around. And I think you can only explain that in terms of, so I repeat, cultural niche construction or niche construction. They're around because we use them. But we are the agents, not the large language models. So that puts a certain, if you like, restriction on the application of active inference, certainly to large language models. It just doesn't apply because large language models do not have agency. They can't plan. However, I think you can still apply predictive coding, because predictive coding does not necessarily have an inactive aspect to it. You can still do lots of good sense making and learning from predictive coding. And in a sense, if you read transformer architectures as if my friend Chris Buckley likes to say, if you can Bayes explain them properly, they do look very much like sort of hierarchical or deep extended Kalman-Bucy filters with really clever attention heads that sort of optimize the Kalman gain in a semi-Markovian way. So the expressed like that, I think there is a source of understanding that inherits from a predictive coding Bayesian filtering view of data assimilation, evidence accumulation, but it's not inactive, in the way that the story that I was telling. Is that what you were driving at, or?
So as far as I could understand you say you agree with me that if you look at the training phase, we can easily use the predictive coding story to describe what is happening there. But as long as our notion of agency excludes artificial systems, which are just reacting on prompts, we cannot use the predictive coding story to describe an interaction between a human and a tool.
That's it. Yeah, well, I think you can, but then the large language model would be the tool. But I think you're right. Predictive coding by itself, which is not active inference closes the circle. But predictive coding by itself, I think, is a very good metaphor to try and understand the computational architecture of large language models. And it goes a long way beyond conventional Bayesian filtering versions of predictive coding, and as you say, into the realm of learning as well, because normally predictive coding is about data assimilation and inference, not about learning the actual parameters or of the implicit state space model. But the same principles can be applied at a slow timescale. I think that's a very useful perspective. Absolutely.
And have you any idea what should happen or could happen that you change your mind and think about whether large language models could be agents?
Well, that's a great question. Yeah, I think that's exactly what people at the moment. Because we don't really have to worry about whether they are intelligent in the sense that we were discussing earlier on. If intelligence entails agency, because large language models don't have agency. But how would you equip them with agency? And of course, that means you'd have to find or engineer a part of the deep structure that had a generative model of the consequences of their action. And it could be internal action. It could be where they deployed the attention heads. It doesn't have to be overt action. And then you start to think now about having a hierarchical a separation of temporal scales within the large language model that can start to recognize its own behavior and start to roll out into the future under different kinds of behavior. So that would, I think, be the line of thinking if you wanted to answer the question: how would you make large language models into true agents? And what kind of actions would they be? Would they start to now test out different prompts? Would this be totally internal, and would they ignore some prompts and attend to some other prompts? What kind of agency would you want from a large language model? I suppose the answer is exactly the kind of agency you'd want from your children. So speak when speak.
Let's go on to
speak when spoken to.
Let's go on to some other
Thanks a lot.
questions. Ankur, sorry, wait. I interrupted Gary, and Virginia hasn't spoken yet. So does either Gary or Virginia want to say something? Because otherwise we have three people that want to ask questions.
I would go on.
Go ahead. Go on. You go.
I mean, in your place, I would go on to the three people who have questions.
Okay, thank you. And Gary, do you suggest the same thing? You're quiet. I cut you.
Yes, please.
Okay,
go ahead.
Ankur Mali, go ahead and ask your question. Can you make yourself heard?
Yeah. Hi, Karl. Can you hear me?
Yes, go ahead.
Yeah, hi, Karl. Nice to meet you. So yeah, one thing which you had discussion with Stephen, right? Using LLMs from the formal language perspective, but transformers. My point was transformers in the sense have limitations, even understanding context-free languages. So don't you think if we are using LLMs based on these architectures to derive the bound for Markov blanket, will lose the credibility of Markov blanket? Like it won't give us the necessary action space which we need to understand the perception and the prediction error of a system. What's your take on that?
I'm not sure I fully understood the thrust of the question, but certainly there is a danger in using transformers to try and learn the right kind of structure and the right kind of deep architecture that would entail a proper generative model and the solutions for which everybody's is searching in terms of the structure of language. And I think that danger was nicely articulated in the second presentation today, that at the moment the learning is using the wrong objective function. I was just thinking about that because one way you could read my presentation is there is only one objective function, and in a deflationary way, it's not even really an objective function. It's just that things that are sustainable, or things that in a sustainable way retain themselves in some characteristic states, can be described as optimizing the model evidence or the marginal likelihood. And the point being made earlier on is that the marginal likelihood of the model evidence has this complexity aspect to it, which is missing in terms of the training objective in current transformers, which means that you have to, because you haven't got that complexity constraint in play, that sort of Occam's razor in play, there are no constraints on how large they can be. I often smile when I hear about large language models, because in the title is a very fallacy. Large, they should be small. They should be small as your children. And I think in virtue of the fact, until somebody puts the right objective function in, which is essentially just equipping the accuracy or the prediction error, if you like, with a constraint on the model complexity, either algorithmic or in terms of the divergence between the poster and the prior. I don't think you're not going to be able to get the right structures out. It's only when you put that complexity constraint and you make it actually the model evidence that you're optimizing, should the structures emerge. I'm sure that hasn't answered your question, but it was something going through my head when listening to the previous conversations. Is that what you were driving at, or did you have some other angle in mind?
Yeah, this is what I was trying, like understanding the complexity and then deriving the learnability, not just based on a single objective function, which does the next word prediction without understanding the language.
Yeah, good.
Okay, thank you. Ben, you can ask your question on condition you say your name.
Sure thing. Hi, Benoit Lepine. I just had a quick question, follow-up question about the agents and LLMs and architectures and all of that. It doesn't really seem so far-fetched to think that we might not be so far off being able to find a successful architecture that would make them true agents in the sense you talk about. And I'd like to know about where do you think we're at in the roadmap you laid out in your white paper about the designing ecosystems of intelligence from first principles. Do you still think we're at the very first phase, or are we progressing on that with LLMs and, of course, whatever work you're, of course, doing with Versus and all those great people?
I still think we're at a very, very early stage. Don't want to, uh, so that roadmap actually spoke to sort of a lot of the key issues that I think we're sort of addressing or are being addressed in this summer school. Just in virtue of the fact we're talking about the primary application of transformer architectures, which is large language models. I don't think it's any coincidence that it's all about the kind of content that that is central to our cultural niche construction, co-evolution. I think they are around simply because they do actually generate language, which is clearly speaks to that sort of the federated ambition of that roadmap. But to be an honest answer to your question is, I think we're a long way away from putting true agency into the incredible and really impressive performance of large language models in terms of generating content. The question is, how would you do that? And I've asked that question before. And what would you want that agency to look like? Now, from the point of view of the white paper you refer to, then the objective, what you would want, is it for to participate in an ecosystem in which there was this generalized synchronization that I was illustrating in the presentation, which is just a joint free energy minimizing solution of all the participants in this information ecosystem or language ecosystem, which means that you would want to, you would expect to see the kind of agency that responded to the affordances to learn about how to integrate and to harmonize or to synchronize with this particular set of users or system of users, simply because from the large language model's point of view, if it can predict how it is going to be used and use, then it's minimizing its surprise and minimizing its free energy. And that in principle is the ultimate and the only sustainable solution.
Okay, we are a short way from the break before the panelists, but not so short, 3 minutes, that that Virginia or Gary cannot have their deferred due. Virginia,
I'll wait until the panel, I think.
panel. Gary, you too?
I can, I guess, make a short comment that just concerning LLMs, and that one of the surprising and remarkable things that I think that I take away from these advances in LLM performance is just how much is learnable without agency. That Karl, as you say, they're not agents, and yet basically through observational learning of agentic acts, largely through language, natural language, the models are learning, and by minimizing surprisal, the models are learning a lot of the structure of the world. They're not learning it in the same way that humans are. They're not learning all the same things we wouldn't expect it to, but that they are learning so much structure at all is kind of without being able to intervene is remarkable. I wonder if you think it's also remarkable, and what's your take?
Are you surprised? Are you surprised?
Yes, but I think you've made the point. But yes, I will fully endorse that. Yeah, it is remarkable. And what I think is it's also a testament to how remarkable language is. If language has evolved to be so rich, a pure observational machine can reconstruct to a certain extent some of the causal structure of our lived world, that's a real testament to the power of language in and of itself.
Yeah. It was good. Steve, it has to be really short, otherwise you can do it in the panel. Go ahead.
Quick comment on grounding the chatbots. There's a number of groups out there, including Boston Dynamics, that have actually put chatbots into robots. And this makes it a little more interesting when you have sensor effector kinds of inputs that are not yet under the control of the chatbot. And there's a number of anecdotal stories about that. I don't have time to tell them, but I urge you to look this up because this is moving very rapidly. Every couple of weeks, there's something happening with robots and LLMs that are kind of, shocking, I gotta say. And that's all I had to say about that.
Okay, you have a microsecond to answer, or you can continue in the panel. Karl.
Oh, that doesn't need an answer. I'm going to go and look up the daily advances in Boston Dynamics and putting large language models into little dogs. That sounds fascinating.
Okay. So thank you very much. Panelists, stay tuned. We're going to be back in half an hour. Okay.